Let's dive right into this explainer and completely dismantle what you probably think you know about the most famous physicist in history. When you hear the name Albert Einstein, your brain almost instantly goes to the crazy messy hair, the giant blackboards covered in chalk equations, and of course, the atomic bomb. But the real story of how this guy's mind completely reshaped our physical universe is so much weirder and, honestly, far more relevant to your daily life than the pop culture legends want you to believe.
Take this, for example. Back in the 1950s, during the height of Cold War paranoia, popular culture genuinely thought that simply assassinating Einstein beforehand would have stopped the nuclear bomb from ever existing. This super dramatic quote is actually from a 1957 sci-fi radio show called X-1, and it perfectly captures the ultimate myth, that Einstein was the singular lone father of the bomb. I mean, Time magazine literally called him exactly that in 1946. But the truth? It's entirely different.
Here's the absolute crucial takeaway. His incredibly famous equation, E=mc², was really just a measuring tool. It was a way to calculate the sheer power of the atomic bullet, but it was absolutely not the blueprint to invent the gun itself. E=mc² just tells us that energy and mass are interchangeable. They're basically different forms of the exact same thing. You really don't need that equation to physically assemble an atomic weapon. So his math completely changed how humans perceive the universe, but it ended up becoming famous for all the wrong reasons.
Part 1. Proving atoms are real.
To see what he actually got right, we've got to zoom way into the microscopic level. Back in 1827, this botanist named Robert Brown was looking through a microscope and noticed the incredibly chaotic, random path of a pollen grain just wobbling around in some water. And for decades, scientists just watched these tiny grains jiggle and vibrate, but literally no one could definitively prove what was pushing them. It honestly looked like magic, and they called it Brownian motion.
Enter Einstein in 1905. He looks at this visible wobbling and has this major realization. He deduces that invisible atoms and molecules must be actively smashing into the pollen millions of times a second. He actually sat down and mathematically mapped out how these totally unseen water molecules were crashing into the larger grain. This wasn't just some clever math trick. It was the definitive, undeniable proof that microscopic atoms physically existed. He basically settled a century-old scientific argument using pure statistical deduction.
Section 2. The photoelectric effect. Now, his next big breakthrough tackled the very nature of light itself, and this is the one that actually won him a Nobel Prize. And, fun fact, it's what currently powers the International Space Station. Let's break this down with a super easy analogy. Think of light hitting a piece of metal like a line of cars approaching a toll booth. If the light particle, which we call a photon, doesn't have enough energy money, it absolutely cannot knock an electron out of the metal. But if it has the cash, the electron gets knocked loose, and boom, you've got an electric current.
We call this the threshold frequency. If the incoming light doesn't meet this exact, specific energy threshold, that electron is not going to budge, period. You could shine the most blindingly intense spotlight imaginable at that metal, but if those individual photons don't carry the bare minimum energy required, nothing happens at all. It's an all-or-nothing quantum transaction. And the really amazing part? This exact principle is the entire basis for how modern photovoltaic solar panels turn sunlight into electricity today.
Section 3. Relativity and time dilation. Okay, so we've looked at the tiny stuff, now let's scale up to moving objects. Einstein found himself staring at a massive contradiction between two absolute heavyweights of physics. On one hand, Isaac Newton had established that speeds are always relative. Like if you're driving 65 miles an hour, that's only relative to the road beneath you. But on the other hand, James Clerk Maxwell proved that the speed of light never changes. It's always an absolute constant of roughly 300 million meters per second, no matter what. You literally cannot have universal relative speeds and a fixed absolute speed existing at the same time without breaking physics. Somebody had to be wrong. So, how did Einstein fix it? With a brilliantly simple thought experiment. He imagined lightning striking the front and back of a moving train. Now, an observer standing perfectly still on the station platform sees both bolts hit at the exact same time. But a passenger on the moving train who is speeding toward one flash and away from the other is going to see those strikes happen at two different times. And the totally mind-bending realization he had was, neither of them is wrong. They are both completely technically correct. Because observers moving at completely different speeds will literally experience the timing of events differently. This leads us to time dilation. It means that if you move incredibly fast through space, time literally slows down for you compared to someone who is standing completely still. Time isn't just a universal, constant clock ticking in the background for everyone.
Space and time are intimately woven together into a single, flexible fabric that we call space-time.
Section 4. Warped space and cosmic ripples.
Let's see how this flexible fabric concept scales all the way up to the cosmos, fundamentally changing how we understand gravity. Forget the idea that gravity is just some invisible magnetic pull. Because space and time are a physical fabric, massive objects like our sun literally warp it. Think of a bowling ball sitting in the middle of a trampoline. It creates a deep valley, right? If you roll a marble nearby, it isn't being magnetically pulled toward the ball. It's just naturally following the curved valley of the trampoline. That is exactly how our planets are orbiting the sun. This trampoline effect was a massive game changer. It boldly predicted mind-bending cosmic phenomena that we couldn't even see yet, and have only recently confirmed with modern telescopes. Einstein's math showed that massive galaxies could warp space-time so much they'd act like magnifying glasses, bending background light. We call that strong lensing. It predicted black holes, objects so incredibly dense that their valley in space-time is too deep for even light to climb out of. And it predicted gravitational waves, actual ripples spreading through the fabric of the universe itself.
And you know what? We found them. In 2015, the LIGO observatories finally detected actual gravitational waves. Two massive black holes collided out in space, sending massive ripples across the cosmos that traveled for 1.3 billion years. By the time those waves washed over Earth, the wobble they caused in our local spacetime was 10,000 times smaller than a single atom's nucleus. But our instruments caught it. The wobble was real. Einstein was right. Yet again.
Section 5. Einstein in your pocket.
Okay, so you might be wondering, why is all this warped space-time and atomic wobbling matter to me on a Tuesday morning? Well, let's look at your daily commute. The GPS satellites guiding your car are orbiting the Earth super fast, meaning special relativity dictates their onboard clocks should slow down. But because they are way up high, experiencing much weaker gravity than we do on the ground, general relativity says their time should actually speed up. You have two crazy physical laws fighting each other.
And when you crunch the numbers, the net result of all that space-time warping is that the clocks on those GPS satellites pull ahead of our clocks on Earth by exactly 38 microseconds every single day. I know, 38 microseconds sounds like absolutely nothing. It's a fraction of a blink.
But trust me, it's huge. Your phone's GPS relies on incredibly precise timing from those satellites to triangulate exactly where you are standing. If software engineers didn't actively use Einstein's equations to mathematically correct that tiny 38 microsecond drift, the errors would pile up almost instantly. Within just a few hours, your Maps app would become totally, hopelessly useless, trying to guide you miles away from where you actually want to go.
From starting out as a humble patent clerk to completely rewriting our reality, Einstein gave us the mathematical rules for the atoms making up your body, the solar panels on your roof, and the GPS in your pocket. Over the last century, literally every test we've thrown at his theories has proven him right. But, as we know, science is all about constantly questioning. So I'll leave you with this pretty wild thought. If the theory of relativity is ever actually proven wrong, what incredible new rules of the universe are we going to discover next?